Welcome to Chemistry with Caroline. In this video, we're going to look at the reaction of alcohols with HX, specifically HBr and HCl. So we'll start with HBr. We've got an alcohol here, tert-butyl alcohol, in combination with HBr. The OH is a poor leaving group, and so in order to get that OH to leave, we're going to have to make it a better leaving group, and HBr is a strong acid, and so we'll be able to protonate that and make it a better leaving group. So a lone pair of electrons on this oxygen atom will pluck off this proton here, and these electrons will go onto the bromine. And that will give me a good leaving group now because I have essentially a water molecule attached to my starting material. And then I've also in the process generated bromide, which is going to act as my nucleophile in this reaction. So now that the oxygen is protonated, it's a good leaving group. And so on a tertiary carbon in particular, it's just going to leave there. So that will give me my carbocation intermediate, this tertiary carbocation, plus my water molecule that is left. So that's the byproduct you see up there. And then again, I have I'm just going to redraw my bromide over here, and I'll draw my one lone pair that I would use. So this is an SN1 type reaction. We generate a good leaving group in the water molecule that can pop off, and that gives us the electrophile or carbocation. And now my nucleophilic bromide can come in and attack, and that gives me my final product there, the bromide, the alkyl bromide up at the top there. So this particular reaction works all right for tertiary systems and some secondary systems. It's pretty slow for primary systems. Tertiary and secondary would be an SN1 type reaction, whereas a primary system would go through an SN2 reaction. Now we'll take a look at the reaction of alcohols with HCl. Chloride ion is less nucleophilic than bromide ion because it is smaller and less polarizable. And so generally speaking, when we look at HCl, it's going to be less reactive, and often we'll use a Lewis acid catalyst in order to speed up the reaction. And so in this case, we're adding zinc chloride. The combination of zinc chloride with HCl and water is called the Lucas reagent. And so in this case, instead of just getting protonated, the alcohol is going to complex with the zinc. It does that more strongly than it does with a proton, so it makes for a better leaving group and a faster rate of reaction. And so one of the lone pairs on the oxygen is going to donate that lone pair to the zinc. The zinc can accept it, so the zinc is acting as a Lewis acid. And that complex is going to make for a really good leaving group. So then down here, I've got the oxygen. It's going to have a positive charge now because it's got 3 bonds. The zinc is going to be negatively charged now. So you have what's called a Lewis acid base complex. But this whole thing is a really good leaving group. And when we go through an SN1 type reaction, the rate is dependent on the leaving group leaving. So this whole complex is going to leave and generate our electrophile. So that would give me this. And now I'm going to have chloride ion just floating around in solution because you have HCl in there. It's a strong acid, so it's going to be dissociated. Now, I also would have, as a byproduct over here, this zinc complex, which would have popped off as my leaving group. So once it leaves, a chloride ion that's in solution can come in and attack, and that will generate my alkyl chloride over there. So again, this type of reaction works best for a tertiary system, then a secondary system, and it really doesn't work very well for a primary system. So the tertiary system is going to go via SN1. It's just too crowded for a backside attack anyway. By introducing the zinc chloride, we can ensure that the secondary system goes via an SN1 because we're making a really good leaving group. Now the primary system won't be able to go via an SN1, and that's where it really matters that we have chloride instead of bromide. For an SN2 reaction, the rate is dependent on both the leaving group leaving and also the nucleophilicity, so the nucleophile. Because chloride is a weaker nucleophile than bromide, this reaction really doesn't work for a primary system. It's so slow that it's not really feasible for it to proceed and make the alkyl chloride. So we typically would use a different method and different reagents if we wanted to get an alkyl chloride from an alcohol and we had a primary alcohol to begin with. So I want to wrap up by drawing your attention to a few of the limitations of this method for making alkyl halides from alcohols, where we use HX as a reagent, so HCl or HBr. These are going to be prone to rearrangement reactions because you have a SN1 type reaction. So since the reactions that go quickly proceed through an SN1, you have a carbocation intermediate, and whenever there's a carbocation, there's always the possibility for rearrangement products, which will be difficult to separate. Because you're heating this reaction generally and you've got a strong acid, there's always the possibility for competition with elimination reactions. So you could end up generating alkenes as side products and not just seeing substitution reactions. And then lastly, the secondary and especially the primary alcohol reactions are pretty slow, sometimes to the point where it's just not feasible to use that to generate an alkyl chloride. So this has been a look at the generation of alkyl halides from an alcohol and HX as an acid. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.